Hi everyone, in this particular session I'm going to discuss how to expand a function of two variables, say f of x comma y, as a Taylor series and a Maclaurin series. To begin with, we'll understand what we mean by a Taylor series expansion. So as you can see here, the Taylor's series expansion of a function f of x comma y having continuous partial derivatives of up to nth order about a point a comma b is given by this expression. It looks very big as such, but if you observe a little carefully and try to group terms, you'll be able to understand, or you'll be able to remember the expansion much easily. Okay, so as you can see here, I'm trying to mark some similar terms for you to understand and remember the expressions in an easier way. So to begin with, we are given a function f of x comma y, and we are told that it has continuous partial derivatives up to and including nth order. And when I say nth order, this n depends on the number of terms that we are going to take in the series expansion. Okay, so the expansion is given by f of x comma y equals f of a comma b. That means you will simply have to find out the value of the function at a comma b initially, and then that will be added with the next two terms, wherein the first term would be involving fx of a comma b. Here fx simply means dou f by dou x, and similarly fy means dou f by dou y. So x minus a into fx of a comma b plus y minus b into fy of a comma b. So you multiply an x minus a with fx of a comma b and a y minus b with fy of a comma b. This will be the next set of terms. And as you can see, why I have grouped these two is because these talk about the first order derivative terms, and correspondingly we talk about the first degree terms as well. So x minus a is one term and y minus b is the other term. Okay. Similarly, when you go for the second order derivative terms, as we know, there are going to be three different terms: fxx, fxy, and fyy, assuming that fxy is the same as fyx. Okay. So accordingly, the terms in the series would be x minus a whole square by 2 factorial into fxx of a comma b plus 2 into x minus a into y minus b by 2 factorial fxy of a comma b plus y minus b the whole square by 2 factorial into fyy of a comma b. Of course, as you can see here, you can actually cancel off this 2 with this 2 and simply write this term as x minus a into y minus b into fxy of a comma b. But for you to understand what the pattern is, I have written this in this particular fashion. So basically, for that reason, I would like to retain this 2 factorial in all these three terms. So when you go for the second order derivative terms, you will have a 2 factorial in the denominator, and if you look at the numerators, this should remind you or make you recall the formula for a plus b the whole square. So if you can recall this expression, this is of the form a square plus 2ab plus b square, right? That is how we can remember these three terms very easily, right? So these are the second degree terms and correspondingly the second order derivative terms. Likewise, when you go for the third order derivatives, there are going to be 4 different derivatives, namely fxxx, fxxy, fxyy, and then fyy. That means you can differentiate f 3 times only with respect to x, or only with respect to y, or you can differentiate f 2 times with respect to x and 1 times with respect to y, and or 1 time with respect to x and 2 times with respect to y. Correspondingly, there are going to be 4 terms, and each of these will contain a factorial term, which is particularly 3 factorial, obviously. Okay, and when you look at the numerators, similar to a plus b whole square terms for the second degree terms, here you have terms in the very much similar to terms involved in a plus b whole cube. So as you can see here, a cube plus b cube plus 3ab into a plus b. So that will give you 3a square b plus 3ab square. Likewise, you can go for any higher degree terms and correspondingly higher order derivative terms. As long as f of x comma y has continuous partial derivatives up to the corresponding order, you can have the expansion of the given function up to that order. Right? So this is exactly what we mean by the Taylor series expansion. And why do we need this Taylor series expansion could be the next question. And the answer to that question is that if you want to understand the behavior of the given function, which is defined at a particular point a comma b in its neighborhood, then this expansion will be valid for all the points x comma y in the neighborhood of a comma b. So that will tell us as to how the function behaves in the neighborhood of a comma b, right? And if you want to know the behavior, you will have to know the expression at a comma b. Okay, I hope I've made you understand this expression as such. And one more thing is that you are trying to express any given function in terms of polynomial function, as you can see here, because you have an x minus a, y minus b, x minus a whole square, x minus a into y minus b, y minus b the whole square, and so on. So you're expressing or expanding any given function in terms of a polynomial function as long as these conditions hold. Right? So this is exactly what we mean by the Taylor's series expansion. Right? Now, a particular case of Taylor series expansion gives you something called the Maclaurin's series expansion. So the Maclaurin series expansion of f of x comma y, of course the condition is the same, having continuous partial derivatives up to nth order, is basically obtained by choosing a and b in the Taylor's expansion as 0. So what you have to do for the Maclaurin's expansion is that you take up the same expression, okay, and in this expression replace every a and b by 0 comma 0, and that will automatically give you the Maclaurin's expansion. So as you can see, the Maclaurin series expansion looks much simpler compared to the Taylor's expansion because you have chosen a and b to be 0 and 0. Right? So this is exactly what you mean by the Taylor's expansion and the Maclaurin's expansion. Fine. I hope you have understood the expansions properly. Now we'll see how to expand a particular function in terms of a Taylor series or a Maclaurin series through some examples. Okay. So to begin with, we'll answer this question. Obtain the Taylor's series expansion of f of x comma y about a particular point up to and including second degree terms. Now the same question is asked in another way altogether. In this particular way, expand f of x comma y equals sin x cos y as a Taylor series in powers of x minus pi and y minus pi by 2. See, here you are told to expand the function about this point, whereas in this question you are told to expand it in powers of x minus pi and y minus pi by 2. Both actually mean the same because, as you remember, of course, this pi comma pi by 2 is nothing but a comma b. That means to say that a is pi and b is pi by 2 because we expand the function about a comma b in general. Correct? So a is pi and b is pi by 2, and accordingly when you go for the expansion, as you can see here, all the terms in the expansion will be in terms of x minus a and y minus b, and that means to say that in this problem we have terms in the form of x minus a, which is x minus pi, and y minus b, which is y minus pi by 2. Okay, so basically both are ultimately two different versions of the same question. Fine. So we'll go about answering this question. So how do we start with? To begin with, we'll talk about a and b here. Whether the question is asked in this manner or in this manner, we say that you can easily claim that a is nothing but a is nothing but pi and b is nothing but pi by 2. correct? A is pi and B is pi by 2. So once we got A and B, so if you look at the series expansion of the given function, whether it is Taylor series or Maclaurin series, what you have to initially do is that you have to find out f of a comma b, fx of a comma b, fy of a comma b, and so on and so forth. And then once you have found all these, you will have to just substitute all these in the expansion. So for that to be done, first we will start with this expression f of x comma y is given to be sin x cos y. So accordingly we will find out f of a comma b. So what is f of a comma b? So replace x by pi and y by pi by 2. So when you have x as pi, this will be sin pi and this will be cos pi by 2. And sin pi, so to start with, this is f of pi comma pi by 2. So accordingly this is sin pi into cos pi by 2, which is obviously 0 because the value of sin pi is 0. Okay, so after we got f of a comma b, we next have to find out fx of a comma b. So before that we'll have to find the general first order partial derivative of f with respect to x. So how do you do this? We'll have to just differentiate this partial with respect to x. So obviously cos y will remain the same and sin x when differentiated with respect to x will give you cos x, correct? So once we got fx of x comma y, now we'll have to find out fx of a comma b, correct? And what is this now? This is going to be cos pi into cos pi by 2, and cos pi as we know is minus 1 cos 180, but cos pi by 2 is cos 90, which is 0, so effectively this also becomes 0. Okay, so this way we have to find out all possible partial derivatives depending on the requirement. So here in the question we are told to go up to second degree terms, so we'll have to find out all possible partial derivatives up to and including second order. So I'll quickly find out all the corresponding derivatives. Fy, now what will happen when you go for fy? Sin x will remain same, but cos y will become minus sin y. So accordingly fy of a comma b will be minus sin pi into sin pi by 2, which is again 0. Okay, you can verify it a little later on. Now I'll go for fxx. Okay, now what do you mean by fxx? Fxx is about differentiating f twice with respect to x. That means you will have to differentiate this function with respect to x. So that will give you, now when you differentiate cos x, that will give you minus sin x, and cos y will remain the same, correct? And correspondingly fxx of a comma b will give you minus sin pi into cos pi by 2, and that is again going to become 0. Of course, don't assume that in every problem you'll get all the partial derivatives to be 0. I have chosen a simpler problem to begin with. Okay, so now we'll go for fxy. What do you mean by fxy? Either differentiate fx with respect to y or fy with respect to x. Okay, so doing that will give me fxy as, I'm differentiating fx with respect to y. Okay, so cos x is going to remain the same, and cos y is going to give me minus sin y. Okay, so accordingly fxy of a comma b, will this be 0 now? you take a as pi, so minus cos pi is what you get, and then this will be sin pi by 2. As we know, cos pi is minus 1, so this will give you minus into minus 1 plus 1, and sin pi by 2 is 1, so effectively this will be 1. So now we have got a non-zero term. I repeat, generally in a problem, none of the terms could be 0 as well. Now what is fyy? Now differentiate this partially with respect to y, and that will give me minus sin x into cos y. Correct? So this is what I have as fyy. I hope I've got all these things right. Fxx, I got this right. Fyy, I got this right. So accordingly, fyy of a comma b is going to be minus sin pi into cos pi by 2. That's again a 0. Okay, now we'll have to stop finding the derivatives for this particular problem because we are told to find the expansion or obtain the expansion only up to second degree terms. Suppose we were told to go for the third degree terms, then we should have found all the 4 third order partial derivatives as well. So right now we'll not break our heads because we are told to find only these. So now what we'll do is we'll go for the Taylor series expansion based on all these things. Remember, as long as you got these stuff right, the rest is very easy. Of what is the given function? F of x comma y about if you're told to find the expansion about this point, then write it this way, or even if you're told to write it in powers of this, you conclude accordingly. So just try answering to the question. So I would say that the expansion is given by, and now we'll have to be a little careful when we are substituting all these things. So the left hand side is f of x comma y, or because the given function is f of x comma y equals sin x cos y, I can specifically take that to be sin x into cos y, and that is going to be equal to, and what will happen in the first term? I will first of all, for your reference, I'll just copy down this expression for you so that I can substitute terms in an easier way. One second, do exactly that. So this is the expansion as such, correct? So accordingly we will have the expansion to be, first of all we have f of a comma b. As we know, f of a comma b has turned out to be 0, correct? So accordingly the first term would be 0 plus the next term is x minus a. When you say a is going to be pi. Okay, so x minus a into fx of a comma b. Fx of a comma b, if you remember, all the terms except fxy are 0. So we'll just remember that and then substitute them accordingly. So x minus pi into 0 is what we get. And then the next term is y minus b. You say b, it is y minus pi by 2. Of course, you might be wondering as to why I am writing all these terms even though I know that each of them is 0. Of course, I know that each of them is 0, but I want you to get used to the whole process. Okay. Now the next term is x minus a whole square by 2 factorial. So it is x minus pi the whole square by 2 factorial. And when I say 2 factorial, it is going to be 2. Correct? and fxx of a comma b is 0. Then the next term 2 into this has to be written properly because this is the only non-zero term, x minus pi into y minus pi by 2 divided by 2 factorial is again 2, and fxy of a comma b, as I said, is 1. Okay, and then y minus pi by 2 the whole square by 2 factorial is 2, and this into 0. And because we are told to go only up to the second degree term, I would say that this just continues and so on, and I wouldn't bother to find each of the other terms. Of course, you can simplify this a little further. In this particular example, as I've been telling you, all the terms except this term are going to become 0. So we'll be having the right hand side as x minus pi into y minus pi by 2, and say that this continues this way, and conclude that this is the required Taylor series expansion of the given function. Right? This is exactly what we are supposed to do in any problem pertaining to Taylor's or Maclaurin series expansion. Okay, so we'll now take up one more example to understand things in a much better way. The next example that I've chosen is about expanding a function, which is in this example e power x into sin y, and we are told to expand this function as a Maclaurin series up to and including third degree terms. Mind you, when we are told to find the Maclaurin series expansion, we will not be told to we will not be specifically told about what point we are expanding, because when we say Maclaurin series expansion, this obviously means that a is taken to be 0 and b is taken to be 0. Right? So remember, when you say Maclaurin series, it obviously means a is 0 and b is 0. Otherwise, you might be told to find the Taylor's expansion, and in such a case, you will be told to expand it about 0, 0. Okay? Of course, as you can see, the same question is asked in two different ways. And in the second question, there is another bit which is asked, so we'll worry about that towards the end of the question, towards the end of the solving of the problem. Okay? So how do we start with? So obviously a is 0 and b is 0, correct? Because we are told to find the Taylor's and Maclaurin series expansion. But in this particular problem, we are specifically told to go up to third degree terms. Okay, so when we are told to go for third degree terms, we have to go up to and including third order derivatives. So keeping this in mind, we will quickly find out all the required partial derivatives. So first of all, f of x comma y is given to be e power x into sin y. Accordingly, f of a comma b, I would specifically take it as 0, 0 because I know that we are going for the Maclaurin's expansion. So this will be e power 0 into sin 0, and because sin 0 is 0, this will be 0. Okay. Next is fx. What do you get fx as? Fx is e power x. E power x is going to remain the same, and sin y is going to remain the same because that's going to be a constant when we are differentiating f with respect to x partially. So what is fx? So this is again 0. I think I've chosen two wrong questions. Okay, now we'll go for fy. What is fy? Now we'll have to differentiate this with respect to y partially. So in this case, e power x will remain the same, and differentiation of sin y will give you cos y. Accordingly, fy of 0, 0 is no longer 0 because e power 0 is 1 and cos 0 is 1, so this will become 1. Correct? Now go for fxx. Of course, as long as you have e power x, it will remain the same how many ever times you differentiate it. So fxx of 0 comma 0 is still 0. Okay, fxy. What is fxy? fxy, differentiate fx with respect to y, and that will give you e power x cos y. So accordingly, fxy of 0 comma 0, that will give you 1 because e power 0 is 1 and cos 0 is 1. And then go for fyy. What will be fyy? fyy will be e power x into, when you differentiate cos y, you get a minus sin y. Okay, so fyy will give you 0. Okay, so I'll write the other expressions as well here itself, so that I can see the previous function and then differentiate accordingly. fxxx is obtained by differentiating this function with respect to x, so that's again e power x cos y. And remember, in the previous question we were told to go only up to the second degree terms. That is the reason we stopped at finding the second order derivatives. But now in this question we are told to go for the third order derivatives, so we'll have to obviously go up to the third order derivatives itself. Okay, so now fxx is over. Now you'll have to be a little careful. fxxy, what do you mean by fxxy? Differentiate fxx, which is this, with respect to y. That will give me minus, I'm sorry, I think I went wrong with this, did I? fxx is e power x. Oh, sorry. I wrote some stuff wrongly. Pardon me. So this is sin y. That is the reason we got this as 0. This is cos y. This is sin y. Yeah. So fxxx is going to be e power x sin y itself. So fxxy will be e power x into cos y, because we'll have to differentiate fxx with respect to y. Okay, so this will be taking the value as fxxy of 0 comma 0 to be 1. Okay, then f x y y. Remember, these mixed derivatives can be found in so many different ways. One way is what I'm going for. So fxyy would be about differentiating fxy with respect to y. Okay, so when you differentiate this with respect to y, that will give me minus e power x sin y, right? So correspondingly f x y y is going to give me 0, because we still have a sine term in this problem. And finally fyy. Fyy is about finding fyy, differentiating this with respect to y. That will give me minus e power x cos y. And accordingly fyy y of 0 comma 0 is going to be a minus 1. Okay, so now these are the partial derivatives that we have got. Accordingly, now I'll go for the expansion. Thus, if I am answering the question according to the first manner, I would have to mention that it is a Maclaurin series expansion. So the Maclaurin series expansion of f of x comma y is given by, yeah, so what will be the Maclaurin's expansion? So once again I'll just copy this expression for you so that you can remember it in an easier way. Okay, so this is what is the Maclaurin's expansion. So accordingly, f of x comma y, that is going to be e power x sine y, is going to be equal to, first term is f of 0 comma 0. F of 0 comma 0, as we know, has turned out to be 0. So the first term is 0 plus, and then what next? It would be x into fx of 0 comma 0. So if you see as to what that is again a 0, and then y into fy of 0 comma 0. Fy of 0 comma 0 is going to be 1, so I'm going to take it as 1. So as I said, if you find out those derivatives properly, the rest is pretty easy. Okay, then next term is x squared by 2 factorial, which is 2, and fxx, if you remember, is 0 again because sin y is remain the same, and then this is 2 by 2, which is 1. That will be xy into fxy of 0 comma 0. What did you get fxy of 0 comma 0 as? Fxy of 0 comma 0 is 1, so this will be this into 1 plus y square by 2 factorial, which is 2, into fyy of 0 comma 0. Fyy of 0 comma 0 has started to be 0. Okay, so this will be 0 plus x cube by 3 factorial, and when you say 3 factorial, this is x cube by 6, correct? And fxx is 0 again. Then when you say 3 x square y by 3 factorial, that is going to be x square y by 2, because 3 factorial is 6, 3 by 6 is 1 by 2, right? And fxxy is 1. Okay, so this will be a 1 here. Then again here you get x y square by 2 factorial by 2 as such, and this will be 0 because we have got fxyy of 0 comma 0 to be 0, and the last term is plus y cube by 3 factorial, which is 6, and that multiplied by fyy of 0 comma 0 is minus 1, so this will be minus 1. And don't forget to say that this continues as such because it's an infinite series expansion. Okay, so upon simplification, this turns out to be e power x sin y equal to, this is 0, this is 0, y into 1 is y itself. Okay, and then this is 0, then xy into 1 is just x into y, and then this is 0, this is 0, and then the next term is x square y by 2, right? And this is minus y cube by 6, and this goes on. Of course, you cannot simplify this any further, so conclude that this is the required Maclaurin series expansion of the given function. Right? So this is exactly how you'll have to work out problems pertaining to Taylor's and Maclaurin's expansion. Fine. So with this, I'm going to conclude with this session. So as always, study well, go through the video completely, and try to solve the problems in parallel, so that you will be able to understand things in a much easier way. Fine. Thank you.